Hi everyone, I'm Nicolas Pita, a PhD student from the Model Force group, and this is a video, part of a series of videos where we want to show you how our group makes the CFD simulations of the Ventricle. Today in particular, we're going to talk about how we do our simulations in the commercial solver Ansys Fluent. So let's start by showing you some of the slides. As I said, this tutorial is about Fluent, and well, the methodology behind the tutorial of today has been done together with in collaboration with the Professor Neidlin. And well, if you, as part of the simulation is based on their previous simulations, you can also go to their video, their website, or their GitHub where they have many material and codes about this. But well, to start this tutorial, we first need to have Python and Spider with pip, numpy, wheel, matplotlib, and scipy installed. Also, of course, all the tools are in Ansys, such as the Workbench, SpaceClaim, Meshing, Fluent, or CFD Post. And finally, if you haven't seen the geometry preprocessing tutorial, you can go now, but we will need the STL files of the ventricle evolution that we created there. If you already have this, you don't have to go to that tutorial. And well, the first step would be to load the given workbench file that we're going to give to you and use it to set up this tutorial. Once we have this workbench, we will open the geometry in a SpaceClaim. This is really important. You have to work with a SpaceClaim, which is not available in Linux. So maybe you need to go to Windows, create the mesh, and then import it in Linux if your working environment is there. But well, we are going to load the geometry. We are going to not convert it in solid by not merging the faces. And this is really important because then in meshing, we are going to open this geometry and name the inlet, outlet, and the ventricle boundaries. So for that, we need that not all the faces are merged. And then we're also going to include some meshing steps so we can get the volume meshed. And well, so let's see how we can do this on Fluent. So, as I said, we start from the workbench. It is important that we load our simulations here so that we don't have any problems with negative volumes and in the moving mesh and so on. So we load this workbench, and then you can save it with your name or your geometry or whatever. And then the first step would be to reset the geometry. So you can upload your own geometry. Of course, if you're working with our own geometry, then you can just skip to the setup or whatever. But in geometry, we open with new SpaceClaim geometry. So now the geometry window should open. And here, as I said, we're going to load the STL file. We have to take care of the scaling of the units that we have the STL file, and then we're going to convert it to solid by not merging the faces. So as you can see, we have opened the SpaceClaim workbench. So here we're going to go to assembly, and we're going to go to file, and here we are going to go to the STL files that we created before in the geometry preprocessing tutorial. We're going to select the format of as STL. As I said, take care of the units that appear here, STL units. In our case, it's in millimeters, and we will load the initial mesh. In our case, we will have called it ventricle 0. So we load this. And as you can see here, we have our idealized left ventricle model. So now the only thing left to do here is to go to facets and convert to solid, do not merge faces. So we click yes, and now that you can see that we have a solid, so now we can close this workbench and start meshing. So let's go back to the workbench. Here, as I said, we have to refresh, so we get the new geometry there. So well, once the geometry is updated, we can right-click in mesh, click edit. So the meshing window will open, and you can see our STL file now here loaded. So first thing would be to declare the boundary conditions. For that, we can use this selection. In our case, we want to select surfaces. And as you can see, if we click, we get a triangle, but if we double click, we'll get all of the plane. So here we can right click and create a name selection, but as I didn't reset the mesh, I already have here declared, so I will only have to apply here. So the inlet gets linked to that surface. I will do the same for the outlet. We click there, and finally for the ventricle we will use the volume selection. We'll select everything and click here on ventricle. So you can see now we have declared all of these surfaces, and we can go to meshing. So in meshing, it is really important, if you restart this, you have to select here, right click in mesh, insert and method, and you will get something like this. And here you have to specify what method do you want. In our case will be tetrahedrons and patch conforming. It is really important that you select patch conforming for the mesh movement to work correctly. So once we have done this, we can click generate, and we'll get the mesh, the volume meshed. Also, it is really important that here you specify your element size. In our case, it's already specified as 10 to the minus 3. But if you want to refine this mesh, or even if you want to include here another method such as inflation, sizing, or whatever, then you can do a more specified or detailed meshing of your volume. But well, in our case, for now, using just patch conforming and this size, we will get this kind of mesh in our volume. So once we have meshed, we can close the window and go back to the workbench. So now we have to update the mesh, and once this will be updated, then we will have to refresh the setup, and then we can start editing the simulation setup itself. So let's go back to the slides and see what the next step would be. So once we have finished the geometry and meshing, we can start Fluent with double precision and the processes that we want to select. And then the first thing to do is to check that the user-defined memory nodes match with the processes that we have selected, since if not, when we execute some commands of the user-defined functions, Fluent will crash. Then another thing to check is the boundary conditions IDs, where if they are different than what you can see here, which are you have to go to the UDF point profile file and change these numbers. And then we will go to parameters and customization, unload the library of the UDFs, then copy the necessary files to the Fluent directory, and compile the necessary files there. And finally, also check that the dynamic mesh is not checked on the partition load balance. Then for the setup, we are going to use pressure-based transient simulation. the model will be viscous laminar. We have to also check the properties of the fluid. And initially, the boundary conditions will be for the diastole, which is velocity inlet, and the outlet will be a wall, since it's closed for the diastole. And finally, we're going to also define some things in the dynamic mesh. So for example, we're going to check that the dynamic mesh is checked, the smoothing and the diffusion are selected there. And in advanced properties, we're going to introduce what we can see here, such as the cell volume diffusion function, the GIMRES for the AMG stabilization. And well, then we're going to also introduce some events, which will be the opening of the valves and the closing for the diastole and for the end diastole and for the end systole. And for that, we're going to read one file we have defined. You can either modify it in Fluent or modify the file itself. And finally, we're also going to create the dynamic measures, which if they're created, we don't have to do that. In our case, in our setup, it's already declared. But if not, you have to create here for the inlet, outlet, and the wall, the measures using user defined and the bend move UDF. So let's go to the workbench. As I said, we're going to go to setup, and here we're going to use double precision, and in our case, four processors. You can either modify it here, or if you edit and open Fluent, first the launcher will start, and then you can also open it. So well, let's open this, and we'll get the following, where we have our Fluent workbench, and here we have our Ventricle, right? So as we said, we're going to start by first checking that the number of nodes in the user-defined memory are the same as our processes. In our case, it's already done, but if not, we'll have to put here the number of processes and check. As I said, if not, Fluent may crash at some point. Then we're going to check also that the boundaries have the IDs that we have declared before. So inlet is 6, outlet is 7, and wall ventricle have to be 5. So everything is all right. So that's okay. And now what we are going to do is go here, manage, and if we have something here loaded, then we will click and unload that. And now we have to go to files, and we will give you these following files here, which are the necessary files where we have the profiles for the boundary conditions, the wall movement profiles, also the Python scripts, and the inlet velocity and outlet flow rate, which we extracted in the previous video of the geometry preprocessing, and the dynamic events. So we're going to take all of this, copy it, and go to our Fluent workbench, Fluent directory, which is in our case here, and we have to see where we have to delete what we have here, all of this, which is just time step, that in your case you don't need it. We are going to also delete all of this, and we're going to copy here the files that we copied just now, and also we are going to copy the STL files that we have created also in the previous video in the geometry preprocessing. So we have here the STL files too, when we run for the Spider, the Python scripts in Spider. Well, we're going to talk about that later. So let's go back to the Fluent workbench, and as we already have copied the necessary files, we're going to compile here user-defined functions, compiled, add, and we're going to select the 3 profiles, which is BC profiles and UDF X dynamic mesh and X points. So, okay, here it is important that you check the use built-in compiler if you already haven't built the UDFs. So we're going to build this, It is also important that every time you build the UDF library, you have to delete the previous one after you unload it, of course. And once this library is built, we're going to load, and you can see here that we have loaded different things such as the inlet velocity profile, the outlet mass flow rate, the event move, and some dynamic mesh executions. So once we have done this, we have to also check that here in parallel in partition load balance and go into dynamic load balancing, dynamic mesh is not checked. So if it's checked, you have to take it out. And so now to start the setup, we're going to start from general. We have to see that here is pressure based, transient. So in our case, that's fine. Then here in models, we are going to see that everything is off since we don't want to use any model, but just the viscous one, and that we have selected laminar. So here in this case, it's already done. Then we're going to go to materials and we'll check that in fluid we have here blood and the parameters of blood, which will be the density 1060 and the viscosity 0.004. And finally, for the boundary conditions here, we have to check that initially we have the outlet and the wall, of course, as walls, and the inlet, we have it as velocity inlet. So in our case, we have here pressure inlet, so we're going to change it to velocity inlet. And now when the window of velocity inlet will open, in velocity magnitude, we have to change this to UDF, in UDF profiles, UDF inlet velocity lib UDF. So we're going to apply this. And we already have declared the initial boundary conditions. And what is left before starting to compute the wall movement is to check that we have the dynamic mesh here activated, the smoothing mesh method selected, and then if we go to settings, we'll see that diffusion is selected, so that's okay. And in advanced, we have to check that we have cell volume, gmres, etc. So if we already have checked all of that, another thing to do here is to go to events, where we're going to declare what events we have. For example, to change the inlet to wall when the diastole ends. And for that, we're going to go here in read, and we're going to select the dynamic events file. So you will see that you have loaded all of the conditions here for the initial time, for the end diastole time, and for each cycle, repeating it. If you have to modify something, it's more easier if you do it in the file itself, but you can also modify it here in Fluent. And finally, we have to check also that in the dynamic mesh zones here, we have these three declared. If not, we're going to go to create edit and create the dynamic zones, which will be in user defined, and we'll create inlet, outlet, and wall ventricle. So if everything is created, we're going to close this, and we can move on to the part where we are going to compute the mesh movement. So for that, let's go back to the slides and see what are the next steps. So, as I said, now we're going to compute the wall movement, and for that, we have to first assign the IDs, and for that, we're going to execute the first assign ID UD certifying function command. This will create a surface file in our Fluent directory, and also it will tell us the number of nodes for each core that we selected. Then we're going to open Spider and run the script that is determining endpoints, which will ask if we need to generate the correlation file. We will just say yes, putting in the command window 1. then a number of faces will appear, which we'll use afterwards in the X dynamic mesh we're modifying. It is important also that we run this on the directory, that the Python script is in the directory of Fluent, and we have the STL file folder also there called as STL. And when running this, we will create the different surface files. Then we will create we will run the interpolation script in Python. This will create the total number of frames, which of time steps for our simulation. So here, in total number of frames in a cycle, we will put, in our case, 500, which is the number of STL files we have. And then we will select how many steps we want to interpolate between each time step. As our simulation, it will be 0.001, the time step. We will select 2 to have this. And then the temporal interpolation method, which in our case is spline, and we'll create the necessary files for Fluent to read the mesh movement. Finally, with the values that we extract from here, such as the number of time steps or the number of all nodes that we extract from each script, we will modify the UDF X dynamic mesh. Then we're going to unload again the library and compile, seeing as we have done in slide 6, we're going to compile again the UDFs. So well, let's go to Fluent again, and we can start doing this. So then, as we said, we're going to go to user-defined functions here. We're going to right-click and execute on demand. A window will open, and we will have to execute on demand. We'll have to choose the first assign ID command. So we will click that, execute, and as you will see here, we will get the different zone IDs and the division of the cells of the volume for each processor we selected. So now that we run this, also surface file will have created here, as you can see, and we also need to copy the STL files that we created in the previous video of geometry preprocessing. So we will copy this STL folder where we have our evolution of the STL files and copy it on our Fluent directory so we can run with the spider the Python script. So once that we have done this, we will go to we'll open a spider, and we will go to we're going to run the scripts for the determine the endpoints, the interpolate the endpoints, and also we will open this other file, which is the X dynamic mesh, execute dynamic mesh, to change some of the things we have here. So, but first, we're going to run this. Once we have the surface mesh file and the STL files, in this directory, they will ask if we want to generate the correlation file. We will say yes by entering 1, and we will put 0 as the frame ID, which is the initial mesh that we have introduced in the beginning of this tutorial and that we have meshed. So in our case, it's ventricle 0, so we will put 0, and you can see here that this will take a little bit of time to run, but we have 24,000 points that we will copy to the file here that I said here, and then we'll wait for it to run. So once that this has run, we will enter now the starting frame, which in our case is 0, and the end frame, which in our case is 599, since we determined in the video we wanted 500 snapshots for the STL files. So now it will create all of the corresponding files in the points folder. So once all of the files are created, we are going to run now the interpolate Python script, which will create the files that we need to for Fluent to read it. So we will run this script now. It will ask us the total number of frames in our cycle, which is 500, as I said, which is the total number of still files, and the number of intermediate frames, which is how many time steps we want to interpolate between each STL file. In our case, as our time step will be 0.001, we want just two steps of interpolation, and we will use the cubic spline for the interpolation. And now again, we have to wait till this finishes running. So now that the file has already run, we can see the total number of time steps of frames after interpolation. We'll copy this and paste it here in the X dynamic mesh file. We will save this, so we already have all these things defined. Here also the scale in our case is 0.001 since it's in millimeters in our case, and you don't have to change anything else. So we'll once everything is created, we can see that in our folder we'll have two new folders, which is points and UDF points. The UDF points are the most important one, where there are the files that Fluent will be able to read. So with this, we can jump to the final steps to finish our setup of the simulation in Fluent. And for that, we're going to go back to the slides. And once we have finished this, preparing the moving wall, we will prepare the solver methods and controls, which are, in our case, the pressure velocity coupling will be coupled, and we will use a momentum-based RHO for flux type. Spatial and temporal discretization will be second order, and we can also check the controls by changing the current number. Then we will also prepare the automatic export, where we want to export the different variables of our flow, such as the pressure, the density, the velocity, or whatever. For the initialization, we're going to go to solution initialization. We will, in our case, we will use a standard initialization with all zeros. You can also use a hybrid initialization. We'll click in initialize. Then we are going to right-click in user-defined functions and execute the second command we have, which is first load mesh. And finally, we will prepare the run calculation section, which in the end we have to specify the time step size, which in our case, as we have interpolated 100 UDF surfaces, we will put 0.001. Then we will select also the number of time steps we will do in our simulation. We can put 1 cycle, 5 cycles, or whatever, depending on the time step. We will also specify this, and also the maximum iterations for each time step that should be enough for convergence. And finally, we will just click in run. So going back to Fluent, we can see here, as we said, first is to define the different methods. So we will use coupled for the velocity coupling. Here you can leave auto select or select yourself the momentum based, the transient formulation second order, and then, as I said, also in the controls we can fix the current number here, the initial. So we have 10 there. Now we will prepare the automatic export, which is here. If you don't have it created, then you will have to create here. And basically, as you saw in the PowerPoint, we will check the cell zone ventricle. We will take the velocity, the vorticity, whichever quantities we want to export. We will export the data every 10 time steps. So we export data every 0.01 time. We can check the file name and all of these things. We'll click OK, and we will have here the automatic export. We can also here define the autosave every some time step, for example, 500 time steps. So we can save one file of our case each with 500 time steps. And well, the final thing is to initialize our solution. So for that, double-click initialization, standard initialization, and we will put everything to 0. We will initialize. Then we will specify execute right-click in user-defined functions, execute on demand, and now it's the other command, which is load mesh. First load mesh. We'll execute this. You will see that here UDF surface 1 was loaded. If you don't get this surface, you will have to initialize and then click again. And then the only thing left is to here specify the number of time steps. We'll put, for example, 1 cycle for our time steps size, which is 0.001, and for example, 30 iterations each time steps. We can also click in step variables or data sampling for time statistics if we want to see these time statistics. And finally, we will click on calculate, and then the simulation will start, and we will start getting the different time steps and values of the velocity, etc. So well, from here we'll be able to simulate with this our simulations and get these different videos of the velocity, the criteria, the vorticity, and with this we have finished the setup of the simulation, and we are able to catch the different features that are in our left ventricle during a cycle. So well, this was all. Thank you all for your attention. And well, if you have any questions, you can look us up on our website where we have our codes, our videos. You can also contact us via email or in the website itself. And well, this was all for our tutorial. Thank you all for seeing the video. Yeah, I hope that it was clear, that we didn't miss anything, or you were able to follow and to calculate the simulation of our left ventricle. Thank you all.